In this video, we're going to look at how we can start sketching parametric curves. Again, keeping in mind that these are trajectories that evolve over time, but of obvious interest would be the path traced out by these curves or by the particles they represent. Again, parametric curves is simply a synonym for vector-valued functions. They can be used interchangeably. Here's our first non-trivial function for vector-valued functions, and just looking at it, it feels like it has some quadratic stuff happening in it, but it's not at all clear how that's going to play out. Anytime we have new rules, like here with a vector-valued function, a new system of looking at functions, it makes sense to go back to first principles. One of the first principles of looking at functions is that we can have formulas, we can have graphs, and we can have tables of values. So if we start here with time as our base variable, our independent variable, and x and y as our dependent variable, then we can imagine selecting a range of values for t, and then seeing what the corresponding xy locations are coming out of that calculation. Since there's no domain issue here, I can plug any real time value in here. What we usually do is start with nice integers or whole numbers, and because we can be negative, it makes sense just to span across 0 anyway and see what happens. When we have -2 for our t, remember that our x is equal to t squared by itself, so that would be 4. And at the same instant, at time -2, our y will be just equal to t, so it'll be -2 itself. Filling in these columns, it's actually easier to use one column at a time and then interpret it later as the pairs. So we're going to go with the x's next all the way down. At time -1, x will be -1 squared, which is +1. At time 0, 0 squared is 0. 1, 1 squared is 1. 2, 2 squared is 4. Now over the y column, y is just equal to t, so that's pretty straightforward. Whatever t is, not x, make sure you're jumping from the left-hand column to the right-hand column here. We're going to end up with exactly the same values as the t's. Keep in mind, though, what we're going to plot is only the x and y values. That is what is involved in the plot command, or the plot process. So here, recognizing that the x's are all positive, we can just focus on that side of the graph. And let's do 1, 2, 3, 4. 1, 2, 3. 1, 2, -3. And we'll clean this up just a little bit here. There we are. So at time -2, but we're not going to show that, we're going to be at the point 4 for x, -2 for y down here. And then at the next time point, we'll be at 1, -1. That's here. Sorry, it's +1, -1 for y. And then 0, 0, 1, 1, and then 4, 2. Then, as with all graphing you've typically done before, we make a little assumption that this graph is not too crazy in between the points that we picked. And again, we know linear functions and quadratic functions don't change that quickly. So what we can do is infer, though it is an inference, we don't know for sure until we did more points, but we infer that the graph looks like that. However, we do have that additional information. So this is the trajectory, but we also know that the point is not at all these, or the object we're following or tracing out is not at all these points at the same time. It's at this point when t is -2, it's at this point when t equals 1, and so there's an implied directionality to this curve. The particle will be tracing out this path from here to here, and we're just seeing a trace of it on this graph. And also there's that element of infiniteness, that this curve would come from potentially all the way out from positive infinity in x here, and come in and then hit the 0, 0 point and go back out again afterwards. We put a bound on it here for practical reasons, but the actual curve that is traced out by this particle is infinitely long in both directions. And that's the essentials, though. We now have a new kind of function where we have t's and we define our x and y's as a function of time. This gives us a view, a graphical perspective on what those functions mean. And what we can see is that the y values are constantly increasing. The x values, looking left to right, are going down first, then bouncing back up. And together they trace out this sideways parabola. Is this still a function? You might be having flashbacks to the idea that this violates the vertical line test for functions. Absolutely. This is a function of two variables, x, y as the outputs, with one variable as the input. For any single time value, this particle is only in one position. So we have to be careful about the kinds of rules that we had before for xy graphs and recognize what doesn't transfer over to this new kind of trajectory. All right, to sketch the graph defined by v of t is equal to 4 cos and minus 2 sine. Interesting. So this has the same pattern as cos t sine t, which we saw earlier, which gave us a circle trajectory. So what we'd expect with these small tweaks to it, this 4 coefficient and negative 2 coefficient, is that we're going to see something like a circle, but slightly changed. Never hurts to guess what might have changed, so think about that for a moment before we dive in. But once you're ready, we're going to follow the same process we did last time and build a table of values. Until we build some intuition, it's hard to judge what the effect of these 4s and negative 2 multipliers will have. So this time we're going to set up a table of values from 0 to 2 pi, and what we're going to do is we'll break it up a little bit more at the beginning, and then we're just going to go to the standard every pi over 2. So notice this gap from here to here is tinier. This is the 45-degree jump, 45 degrees, and then 90, 90, 90 as we go around the rest of the circular-ish thing. Where does that leave us? Cos of 0 is 1, and then we're going to have 1 times 4. That'll be 4. Sorry, we should emphasize that this is the x-coordinate formula, and that is the y-coordinate formula. For y, sine of 0 is 0, so that's going to be 0. So right away we know we're in a slightly different territory. In particular, what we had before was a unit circle with radius 1. Now what we're going to have is something obviously not radius 1. 1, 2, 3, 4, x and y. We are starting at 4, 0. What about the next point, pi over 4? Well, I'm going to do a little aside here. That cos of pi over 4 is 1 over root 2, and that's approximately 0.7. We can have more decimals if you like, but when we're graphing on this resolution here, that's going to be plenty accurate enough. And so this value here is going to be around 4 times 0.7, or around 2.8. Meanwhile, sine of pi over 4 is conveniently 1 over root 2 as well, and also around 0.7. So we're going to have here negative 2 times 0.7, and that's going to be around negative 1.4. So that puts our next coordinate at 2.8. It's close to 3. Here's 2. And down instead of up, and down around 1.4. So there. Negative 2. And then as we keep going, when you hit pi over 2, cos of pi over 2 is 1. Sorry, cos of pi over 2 is 0. And sine of pi over 2 is 1. 1 times that multiplier at front is negative 2. So not too surprisingly, we're going to continue this circular type trend. We're just going to reach the most extreme y value here of negative 2. Then we go to pi, cos of pi, reach for your calculator if you need to, is negative 1. Oh wait, but it's times 4, so we're going to get negative 4. And sine of pi is 0. And I think you can start to see some of the patterns emerging here. We started at 4, 0, then half a cycle later we're at negative 4, 0. Not too surprisingly, when we go to the next step, sorry, we should add that to our graph just for thoroughness here. When we go to the next step of our graph at 3 pi over 2, we're going to be at cos of 3 pi over 2, which turns out to be 0, and sine of 3 pi over 2, which turns out to be negative 1. But it's not just negative 1, it's negative 1 times that leading negative 2 out front, and so we get positive 2. And so we see again that alternating 0 minus 2 to 0 positive 2, 4 0 to minus 4 0. And that puts us exactly where we'd expect to be if this was a circular type pattern. And last but not least, at 2 pi, we're going to end up exactly where we started. So again, filling in the blanks here with our intuition and knowing that sine and cos, we've captured the most important ingredients about sine and cosine's change. We expect to see this kind of shape. And if we add the arrows of directionality here, we would be traversing this trajectory in a clockwise manner here, based on this change of the sine coefficient to being -2. That flips things vertically somehow on us. And instead of going counterclockwise, we end up going clockwise. It takes a little more evidence than we have here, but this is in fact an ellipse with axes of 4 long and 2 long. Starting off with our circular pattern of simply cos t and sine t, we can expand it or stretch that in both the x and y direction separately and get an ellipse with the axes dimensions that we like. So it becomes a very easy way to construct more interesting shapes than simple circles, but using circles as a platform to build off of. Finally, for the series, let's involve some more interesting functions like the square root function and the 1/, the reciprocal function. And what arises in this particular example that wasn't in the previous ones is the issue of domain. In the last case, let's just flip back quickly, there was no t value that is a problem for cosine. Cos is defined for every value of t. Likewise, so is sine. However, root t is only valid or only defined for t's greater than or equal to 0. 0 is okay, square root of 0 is fine, but negative anything is bad. And 1/t is only valid for t bigger than 0 and t less than 0. T can't be equal to 0. I'm not allowed to divide by 0. And if that's the case, what we have for the domain of S is the intersection, if you like, of those two ingredients. So I can have 0 or larger, and I can have strictly larger than 0 or negative. Well, the negative doesn't work with this, so we rule it out. And the equals doesn't work because I can't do 1/t for the equals 0. So we end up with t strictly greater than 0. Well, that informs our choice of values for our table of values. So what we might want to do here is be a little more careful about our selection of t's. Again, remembering that the x coordinates are going to be given by root t and the y coordinates by 1/t. So focusing in our domain of t larger than 0, we could start just past 0, which would be like 0.000001. Well, let's take a more straightforward choice around 0.1. Then basically we're going to center ourselves around 1, I think, just to see what's happening. So let's go 0.2, 0.5, and then 1, and then 2, and then 5, something like that. Actually, we have square roots, so let's make our lives a little bit easier and go 2, 4, and 9. Then we'll get some nice values for some of the coordinates. So x and y. One of these is straightforward. Let's do it first in the interest of faster calculations. 1/t is our y value. So if t is 0.1, type into your calculator or do fractions, we're going to get 10. T is 0.2, 1/0.2 is 5. 0.5 is a half, 1/1 is 2, and 1/1 is 1. And then it gets even easier because it's just 1/2, 1/4, and 1/9. Done. All right, square roots. Again, start with the easy ones you can do by inspection. Square root of t, square root of 1 is 1. Square root of 2 is square root of 2. But for graphing purposes, that's around 1.4. Square root of 4 is 2. Square root of 9 is 3. Now, these other ones we definitely do need our calculator for. So we'll pull out our Casio 991s, and we get square root of 0.1 is around 0.3. And again, we don't need precision here because we're not able to graph that accurately. We're simply looking for trends at this stage. I'll put 0.44 there. Should be, okay, I can't let it go. It'd be 0.45 if we rounded correctly. And square root of 0.5 is going to be 0.7. And that provides us enough information, and notice everything here is positive. So this time it makes sense to build our axes in the vertical direction, or sorry, in the first quadrant. So our x's and y's go like so. And we have to go up to 10, oh my goodness, and 3, 2, 4, 6, 8, 10. There we go. So 10 and 10. We start off at y is 10 and x is 0.3. So this is 1, that's 1. So we would be up here. Then 0.45 and 5. The y drops quickly. 1, 2, 3, 4, 5. But it's still in that same 0 to 1 x range. Then we get a little closer to 1 over here. And then we're at 1, 1. Then about 1.4 and a half. Then 2 and a quarter. And here it gets kind of fuzzy. 3 and 1/9. So the implied trajectory through these points shows up like so. Again, it has a directionality. As time increases, we're going to be heading down this curve and out towards these extremes. We aren't going to cross that axis. We're going to stay above it, given the structure we have for our formulas here, but we're going to get that kind of trajectory. Now, what we can feel is that somehow the speed here is changing. And this is a little less clear because we didn't use even time points. But just as a quick example, we're going to go back to MATLAB and just use these formulas for our position functions. And we're going to use this kind of range for our time values. And we'll see how that plays out in an animation. What we have here is a modification of the earlier animation script for the circular motion. And the only real changes we had to make were the square root changes and the 1 over t changes. The other ingredients that were helpful are setting the x-lim and the y-limits, so we actually get the same dimensions, the same range as we had in this plot here. So if we run this script, what we see is a very quick drop, and then thinking about the time values, it took 1 full second to go from 1, 1 to 2, 1/2, or root 2, 1/2, another second to get to root 3, and another 7 seconds to get all the way out to 9 seconds, or x equals 3. We're just going to run that again. And so what we see is very fast motion followed by slower and slower and slower motion. Again, the trajectory is one thing, but just showing that hides some of the other important information about the particle moving on that trajectory, which is the speed and velocity and acceleration, all those other important physical quantities that are best seen through an animation, or also seen through an animation procedure. Fast motion, then slower motion in this case here.